Yeah, good afternoon, everyone, and welcome to this talk on a very important matter. The Matter standard is a unifying solution to provide communication and security in devices within the smart home. It is a freshly developed standard, and in this talk we are going to discuss the security issues that we have found within this protocol. My name is Jan Gabela. I am a senior security researcher at Bitdefender. I have been doing research on Matter since the first devices came out to the market, which is about 2 years now, so the field is quite fresh. I also have an academic teaching research background for about 20 years now. This is a high-paced talk, and because this is a freshly developed standard, I will provide introductory thoughts on the way to motivate our research regarding the smart home. I will also go into the technical background regarding Matter and the Matter ecosystem in order for you to understand our security findings, and I will conclude with some thoughts on the way forward. This presentation is accompanied by a white paper that will be released after this conference. Now, why should anyone care and perform research on the smart home? Well, for starters, the smart home nowadays is not only about light bulbs and smart switches, as one would think, but it is getting to resemble more and more to what is known as the smart factory. So similarly to the smart factory, you will find lively processes, home appliances that are communicating, exchanging data, and participating in automation. Also, within the smart home nowadays, you will find a wide variety of devices, such as EV charging stations, smart batteries, heat pumps that are critical in maintaining the lifestyle of modern users, and that also are transforming the smart house from an isolated environment to a connected system that can impact the operation of other devices that are connected to the power grid at a local or regional scale. Also, the architecture of the traditional IoT ecosystem is changing. So normally you will buy one device from one vendor, and then you will buy a couple of other devices from other vendors, and then you would realize that these are talking different protocols, and then you need applications and other devices in order to translate from one protocol to the other. At the end of the day, you may also end up with a gazillion of protocols and devices and not really knowing how to make them talk to each other. From an attacker's perspective, things are also quite challenging, or can be quite challenging. One day you are doing research on Z-Wave, buying a Z-Wave sniffer, looking into the Z-Wave protocols and ecosystems, and the other day you are required to go into Thread or another environment, and you need to buy another equipment, learn about other protocols. So this can be, from this perspective, quite an interesting view. But our life is getting much easier, both users and attackers' life. With the new Matter standard, we are going to have interoperability between different devices, and this means that all devices within an IoT ecosystem will run the same protocols, will run the same technology, and you'll have the same core code, maybe, that runs on a light bulb, as well as on an EV charging station. So I think that things are getting quite interesting. Now, in the beginning, Matter started in 2019 as a collaboration between 4 companies and the Zigbee Alliance. It is nowadays being developed by the Connectivity Standards Alliance. It is an application layer protocol. It runs on IPv6. It's open, so you can check the standard. You can also check the implementation. It runs on well-established protocols such as Bluetooth for initial commissioning, as well as Wi-Fi and Thread in order to perform data exchanges and later commissioning into other ecosystems. Now, I think that everybody has heard of Wi-Fi. I would like to say a couple of words about Thread. Now, when Matter started out, it started out with the support of Zigbee, but it doesn't really use Zigbee for communicating with low-power and mesh networks. It uses Thread instead. Now, Thread is an IP-based protocol, which means that all of your devices in your smart house will run on IP, so you can just try out any protocol that runs on top of IT and see what happens. Now, in order to translate from Wi-Fi or other protocol to Thread, you'll have to use a Thread border router. Thread includes distance vector routing, it includes security. On top of the Thread stack, you will find different application layer protocols such as HTTP, CoAP, and many other. Now, Matter today has reached a staggering collaboration of more than 600 companies. It is not only a communication standard, but it also includes certification programs. It is getting to be a global initiative that wants to be the single and most established standard for IoT devices. Now, when it first came out, it was supporting only a couple of basic devices. However, with each new release, it supports additional devices. It is supporting new types of devices that are getting more and more complex. We are actually seeing this shift in Matter. While it started with simple devices such as light bulbs, smart plugs, and motion sensors, the latest news is the support for the home router. This means that your home router may also run the same core code that is running on a light bulb. Also, it is supporting EV charging stations. It is supporting different types of utilities. So these are all going to run the same type of technology. From an attacker's perspective, this is great because, okay, you may not have the funds to buy an EV charging station, but you can start off from a very simple device, an outlet. You can start off from a light bulb that is running Matter, and then you can see if you have the ability to break something, to find vulnerabilities, and then if those vulnerabilities may also apply on other devices such as home routers or more critical devices as well. When we first started out, we were quite surprised of the silence that has been in the field. There were no security reports, security investigations concerning Matter, so this was a very good incentive for us to go ahead and see what is going on with these protocols. This year we have started to see some papers showing up, and I think that we need to make some noise and we need to see what is going on in order to ensure that we have a robust standard ahead of us. Also, from a complexity perspective, Matter includes a lot of messages. It's quite chatty. It uses modern cryptography, so this was also quite interesting for us to learn how battery-enabled devices or simple devices in general handle these complex operations, considering that these devices are not only part of the smart home, but can be found in smart factories, smart cities, and in many other ecosystems as well. Also, considering that these devices are using IP-based protocol, just think of it like this. You can just throw any type of attack, any type of packet against these devices, and they should or not respond depending on the case. So we're also interested in learning what will happen if you just throw all those IP-based attacks against these new devices. So as we are going to see, it only takes one vulnerability in order to transform the connected home to a disconnected home in order to disable all devices within the smart home that are running a certain version of Matter. So today we are going to learn about this game-changing Matter standard, and we are also going to learn about the first publicly reported vulnerabilities in the Matter SDK. These involve a new type of attack that we have named delayed denial of service, which can disable all Matter devices that are running a certain version of the Matter standard. And also, we have found and developed a new type of feature scanning attack that can be used in order to map all kinds of Matter devices and features within a certain Matter ecosystem. But first, we need to understand the basic concepts, and in order to ensure that we are talking the same language. So while Matter is a protected ecosystem, it uses multicast DNS in order to discover devices. So you can just use multicast DNS and interrogate for Matter-specific services in order to detect and discover all devices, as well as certain details for devices such as IP addresses, vendor product IDs, depending on the device. These will publish more or less details. Now, the core protection element in Matter is the fabric. This is actually a collection of devices that share a trusted root. So the trusted root is used in order to issue node operational certificate for each device that is added to a fabric. And within a fabric, nodes will use the certificate authenticate the session establishment protocol in order to establish a secure session and in order to exchange data securely. Now, within the case protocol, the integrity protection key is used in order to guarantee certain properties. This is a symmetric key. It is only used in certain messages. A very cool aspect with Matter is that it doesn't really lock devices in one fabric. This means that you can buy a device, create a fabric with Google's technologies, and the device will not be locked into that fabric, but you can add the same device into another fabric, created maybe with Apple's or another technology, and the same device will be able to participate in automations at the same time in more than one fabric. Now, another aspect that is very important is the SDK. So the SDK is the reference implementation of the Matter standard. This includes the code as well as the tools necessary to generate the code for a certain device. This also means that if you have an issue within the SDK, this issue will propagate to all devices that are running the same version of the SDK. In terms of commissioning, this is a term that involves adding or joining of a device into a fabric. The device will open its commissioning window while providing a pairing code that can be used by a controller in order to add the device to the target fabric, where it will receive a node operational certificate, and it can then establish secure communications with other devices. Yes, you can also play around with different code with devices that are not certified in order to test the protocol, in order to test the ecosystem. Some controllers will complain that these are not certified, but you can add them to real fabrics and then see what happens with your devices and your ecosystem. Now, last but not least, I would like to say a few words about the case protocols. This is used for mutual authentication and to negotiate session keys. It is based on the SIGN and MAC family of protocols, and it includes 3 messages, codenamed Sigma 1, Sigma 2, and Sigma 3. Now, when we first started out to look into this protocol, I was at least expecting a very simple, academic, informal description showing all the steps and all the components of this protocol. However, instead what we got were data structures, textual descriptions, some symbols were not quite well defined or were missing, so we were quite puzzled from this perspective. But then we went to the specification, we also went to the reference implementation, and we finally grasped what is actually happening with these Sigma messages. And here we have unfolded the 3 Sigma messages without the optional components. Now, in the following slides, we are going to discuss the first message, the Sigma 1 message, which is the most important from our perspective for our research. Now, the Sigma 1 message is sent by the initiator to a responder in order to initiate a session establishment. It contains 4 mandatory components, 3 of which are random. So the initiator's random and the session ID, as well as the ephemeral public key, are random and cannot be verified by the responder. The only component that can be verified is a destination identifier. However, this is not actually a full identifier, but it is the result of applying an HMAC on the random, initiator's random, on the fabric root public key, on the fabric identifier, as well as on the destination node identifier. Now, in order to validate this Sigma 1 message, a recipient, remember, that can be part of several fabrics. So it will have a fabric list, and for each fabric, it will store the root public key and the node operational key that it received while joining the fabric. Now, in order to validate the Sigma 1 message, the recipient needs to step through all these fabrics and recompute the destination ID, considering the random that it received, the root public key, its fabric identifier, as well as its node identifier. And then with this newly computed destination ID, can check if it matches the received destination, and then it can validate the first message. Now, what about Sigma 1 replay protection? Well, unfortunately, the first message doesn't really contain cryptographically protected message freshness. The message counter is actually the only component that is used, and it is part of the Matter headers in order to ensure freshness, but we can change this message counter, and the recipient will validate this replayed message. So this concludes our introduction to the Matter ecosystem. We are now going to see the details of our testbeds. So we played around with controllers from Google as well as from Apple. We also created our own controllers by using the Connected Home IP project. We also created our own device that we added to a fabric in order to implement and test for this feature scanning attack. These implementations are based on C++, but if you like another language, you have Rust and JavaScript variants that are being developed. In terms of border routers, we used routers from Apple as well as from Google. We played around with devices from that were thread-based, as well as the Wi-Fi devices that were available at that particular time in our testbed. Now, this is a layout of our network. On the left-hand side, we can see a border router from Apple, as well as devices that have been added to Apple's fabric. On the right-hand side, we can see a border router from Google, as well as the devices that have been added to Google's fabric. On the bottom, we can see our own controller as well as our own device, and we can see that devices have been added to multiple fabrics in order to test for opening case sessions and to perform different interrogations. Now, next we are going to go into this new type of attack named the delayed denial of service. So when we first started our research, we were actually motivated, as I mentioned, by the complexity of this protocol, and we were also motivated by the lack of cryptographically protected freshness, as well as by the fact that this protocol is running on IPv6, so you can just throw any type of attack and see what happens. So we were also quite intrigued by the fact that when a responder receives a Sigma-1 message, it can only validate based on the structure as well as based on the destination ID. And then in order to generate the Sigma-2 message, it needs to generate ephemeral public-private keys. It needs to sign and encrypt. So there's a lot of operations and complex operations that need to be performed in order to issue the Sigma-2 message. So this is a very good incentive for testing for the denial of service attack. What we were actually expecting was to get battery depletion at most. However, we got a very interesting behavior. Actually, during the first days, nothing was really that interesting. Nothing was really happening. We were in the lab. We were testing for connectivity with devices. We also saw that controllers were able to switch on, switch off devices while the attack was running. However, when we came back to the lab the next days, we could see that devices are disabled and we are not really capable of opening case sessions with these devices anymore. And then we realized we are in the presence of something very, very interesting. We actually saw that we managed to exhaust the device's capability to handle new case Sigma messages, and at the same time, Sigma case sessions were not really affected by our existing case sessions. So how do you implement this type of attack? Unfortunately, very simple to run. So first of all, you need to get your hands on a Sigma-1 message. Unfortunately, these messages are not broadcasted, but we can rely on MD&SSD poisoning. Remember that controllers and devices within the Matter ecosystem are able or can be discovered by using MD&SSD. So you can query for Matter devices in order to discover their IP addresses, in order to discover other details. So you can just respond to a query from a controller with your own IP address, and then the controller will deliver the case Sigma-1 message to you for free. Also, while running the attack, you only need to replay it 2 packets per second, depending on the device, and we will see that existing case is not affected. This means that while the attack is running, users cannot really know that they are being actually attacked. While the attack is running, interesting behavior is that we cannot establish new case sessions. This actually affects all Matter devices and versions. However, after the attack is stopped, in certain cases, new case cannot be established. This means that you lose connectivity with all these devices. You lose all automations within your home if you are running Matter devices that have a certain version. We actually took this vulnerability and reported it to device manufacturers, and they mentioned that the issue is in the SDK, so it actually affects all devices of a certain version. So we went to CSA and reported the vulnerability, and it was confirmed that it affects all devices running SDK version less than 1.1. And the solution is actually to update to at least Matter 1.1 or to patch the code. Now, upgrading to a superior Matter version is great if you are capable to do so. However, this is not possible for all Matter devices, depending on your capabilities, depending on the available flash, RAM. New and superior Matter versions require additional entries for access control, additional support for groups, group keys, which need additional flash and RAM, so it's not always possible, unfortunately. You cannot really download more RAM or flash. So we propose to change the input of the HMAC computation with the message counter. So this would actually increase the input of the HMAC by only 4 bytes. And instead of having to use and capture 1 sigma message, the attacker would need to capture 1200 sigma 1 packets, which would also increase the attack complexity. Now, this cannot be really implemented yet in practice because Matter doesn't really have version negotiation, and because of this, it will also break backward compatibility. So you are unable to upgrade, you are unable to change the specification or integrate other protection mechanism. What we can do, we can see if we can integrate within the smart house in certain ecosystems, monitoring and detection solutions. This might make sense in the case of critical devices or in the case of systems where we have many devices in place, such as smart buildings. Now, in order to monitor and detect, there is very good news. You can detect the presence of sigma 1 messages by only looking at Matter headers. These are not encrypted, so you can extract the type of packet and count these packets and detect the presence of this DeeDoS type of attack. We have actually implemented a prototype for this detection. As we can see on the left-hand side with the red, we have the DeeDoS attack in progress. And immediately as the attack starts, we have an increase of probability detection up to 100%. We have also played around with reconnection of different controllers, normal reconnection, which would issue sigma 1 messages. And as we can see on the right-hand side, this would not affect the probability, which would stay at a level that's below 10%. Now, what about our initial assumption or question of battery depletion? Well, it is feasible. It only takes 6 to 12 days to deplete battery of devices depending on the device type. So it's important that we monitor such devices to stop early these attacks. Now, this concludes the presentation regarding the first vulnerability that we have discovered. We are going to shift gears and go into the second vulnerability. Remember that Matter is a protective ecosystem. We wanted to test if you are able, within a Matter protected ecosystem, which is a fabric, to scan and find devices, clusters, and attributes, so to map the type of devices that are within a certain fabric. So these are the steps we have followed. We created a virtual device. We added the device to a target fabric, and then we started to interrogate for other devices, opening case sessions and issuing cluster attribute interrogations. For this purpose, we created a virtual device using the Connected Home IP project, used the chip lock application. We added to a target fabric using the QR code. And of course, the controllers complained that these are not certified, this is a not certified device. However, we were able to add it by selecting the Add on Anyway option. Now, the next phase would be to actually connect with a case session and interrogate devices, so this should be very easy to do. However, we have found that there is actually no documentation on how to open a case session. There was no documentation on how to interrogate devices, so we had to go to the reference implementation and find the necessary header files, the necessary objects that had to be used in order to perform this operation. We have all of these details within the white paper. I will not go too much into them, but we added we created an application where we added these necessary include files, also the callback functions when a case is opened, and also we changed the triplock application input to accept a new command, the run scan command, which will initiate the scanning of clusters and attributes in target devices. And this is an example of scan code which looks for available clusters and attributes in a target device. You compile the application, you run it, and then issue the scan command by providing also the target node identifier. Now, unfortunately, after all this, we only got one error after the other, and we realized that we actually rediscovered Matter's built-in access control, which is deny all by default. But all is not lost, so we observed that there are actually two errors that were returned, the unsupported cluster and the unsupported access. And if you look at the specification, you'll see that the first devices verify for the availability of certain cluster and attribute. If these are not available, then the unsupported cluster error is returned. Otherwise, if these are available, then the device will check for access, and you will get the unsupported access error. So this means that we were able actually to infer all the clusters and attributes that were supported by a device by interpreting the returned error values. We went to CSA and reported the vulnerability, and they mentioned that indeed this is applicable to all Matter versions and devices that were available on the market, and is actually resulting in a change in the Matter specification, so we have these changes added to version 1.4. Now, what can you do if you are outside of a fabric and you still want to monitor for these types of attacks? What we actually found was that Matter traffic is quite static, so by looking at public data, looking at the message length, by looking at headers, you can infer with a certain probability what is happening inside the fabric. And this is what we have done. We have gathered all these public details on each packet, and we have built the Matter packet fingerprint. This is actually a string that contains all the details that are publicly accessible outside of a fabric, involving Matter message length, flags, security flags, and all of those details compiled into one string. If you want something similar, you can find in JAW3, JAW4 strings that are applicable to TLS client and server hello headers. Now, this is an example string that includes the packet length, message flag, security flags, and all those components that are publicly accessible are compiled into one string. Next, we looked at encrypted Matter traffic, and we created the Matter packet fingerprint on each of these packets. We also looked at different traffic in time. 1 minute, we captured 5 minutes, 10 minutes after the establishment of a case session. And we have seen that certain patterns are repeating, certain fingerprints are actually repeating. And when we also plotted the feature scanning attack, we see a large outlier which corresponds to these packets that are used for a feature scanning attack. This means that you can actually apply any type of statistical approach in order to detect this type of attack in a timely manner. We can see here with the red line that the cumulative distribution of the feature scanning attack is quite distinguishable and therefore can be detected relatively easily. But I would like to also mention that this is very sensitive to the magnitude of the attack. So if the attacker uses fewer features, if it scans fewer features, then you may have some trouble detecting this with these type of statistical analysis. You may want to use more complex graph-based or even machine learning in order to detect interdependencies and changes within the Matter traffic. Now, this concludes also the presentation of this second vulnerability. I would like to say a few words on the way forward. I believe that this talk should be viewed as a call for action for both offensive and defensive security research. I think that this is a freshly developed standard. It is still early. We can shape the evolution of the standard so that we are free of any major vulnerabilities. Also, considering the NIS2 and CRA directives, I think that we need to look into available solutions for monitoring within the smart house. also make sure that we report and take part in ethical vulnerability management processes. Now, similarly to Matter, there were other protocols as well in history that have promised unification and robust security feature. If you just remember OPC UA in the industrial sector, there have been many vulnerabilities reported that were due to misconfigurations, different errors. So let's not go down the same path again and make sure that we have a robust protocol design from the ground up. Now, what we have actually learned from doing this research is that we need a better description of security protocols in order to facilitate analysis. We also need to make sure that there are more papers, more research published regarding the Matter protocol, and also need to look into available solutions to monitor Matter traffic within the smart home. A few key takeaways. I believe that Matter is a nuclear blast protocol and standard because it will reshape the user's smart home, as well as from the attacker's perspective. With one vulnerability, an attacker might be able to disable all devices within the smart home ecosystem. I was also quite surprised that after 30 years of formal security protocol analysis, it was so easy for us to disable devices. And last but not least, be the one that improves the standard. We had a very good relationship, let's say, with CSA. We thank them for solving these issues in a timely manner, for responding in a timely manner. So be the one that improves the standard by challenging the protocol security. Thank you. We have time for questions if there are.
Hi, Thibault from Monzo Bank, so definitely unrelated to Matter, but I have Matter devices at home. Do you think the protocol has been designed properly to allow or to prevent ossification? Like we've had HTTP 1, HTTP 2, we're struggling to get away from those. And HTTP 3 is meant to be the solution, but we're stuck with routers and stuff in offices and ISPs that don't understand HTTP 3 and just do deal with HTTP 1. And so we can't make HTTP stronger and more secure. Do you think Matter and Thread have been designed properly to prevent ossification, meaning that it's going to be really hard to move away from designs that are preventing us from being more secure?
Yeah, thank you. So Matter has been designed with integrity and authenticity protections. So it uses state-of-the-art algorithms in order to verify authenticity of messages. It includes signing and also verifying signature certificates, so it's very complex ecosystem. On the other hand, what I haven't seen yet is studies that are more focused on the large scale. So for instance, studies on having 100, 500 devices in one network. What will happen considering the low bandwidth available in thread networks? So these are still questions that may require more going into depth in order to be able to answer them. But yes, Matter uses well-established cryptographic algorithms, so it should withstand these types of basic, let's say, forging and man-in-the-middle attacks.
My question was more about, you were talking there's no protocol negotiation, for example, and
version negotiation.
Version, sorry, and backwards compatibility becomes hard, and I've generally that means that evolving the protocol when we find design faults, so not just like, oh, there's a thing we can fix it, but literally how it was designed is the problem. Do you think that kind of thing is going to prevent evolving the protocol as it needs to as we find vulnerabilities, to reshape it and make sure that not everyone has to upgrade their IoT devices every year or two just to upgrade to a new version of the protocol?
Yeah, definitely. So this is a an issue. So if there is a major vulnerability that is found within the case protocol, then this will be, I think, very difficult to address because you don't have, at least if it concerns the standard, then it will be very difficult to address. If it concerns the implementation, then yes, you should be able to address by code patches or updates that can be applied and usually are released by vendors. So vendors need to release code patches and to address vulnerabilities. This is a requirement for having devices certified. So you need to have the life cycle of the security life cycle implemented and in place in order to have devices certified. Yeah. Other questions?
Okay, nice to meet you. I'm Marcello Maugeri, and I'm running the Fuzzing Matter project. I have a bunch of students following me. I published a white paper, and what I'm doing is fuzzing the protocol. So I'm using the chip tool as baseline and sending commands. We had already some results, but what I want to know from your perspective, as you know really well the protocol, what would you expect as vulnerabilities? In sense of that you can trigger by sending malformed commands. So would you expect like buffer overflows or some memory corruptions in general? Or do you think there could be something else that we could look at and prepare a monitor for that specific kind of bugs?
Well, it is great to hear that someone else is doing work in this direction, so thank you for your question. I don't know what you could expect. This is something that we are also looking into, so the next phase for us also is to look into these types of tests to see what will happen with these devices. I'm curious about these new devices that have been released, for instance, the home router access point. It was announced in November. However, the code is not yet available, so the next phase, I think it would be interesting to look into more complex devices that are running the more recent Matter versions, because we know that older versions have these issues. So we are still expecting the code to appear and to have some example devices, and then I would look into these new devices which are much more complex, and maybe you will find something interesting there.
Thank you. Yeah, okay. Thank you.
Question from another home automation user. I was wondering what's the difference or how it interacts with the previous generation, like ZigBee type of home automation. And if your attacks, for example, can apply also to those border routers that do the translation between the two protocols. Yeah, what's your point of view on that?
Yeah, thank you. Great question. So what's important with Thread is that these messages are forwarded by border routers directly to devices. So we have tested these DeeDoS attacks. It also works with Thread devices because messages are forwarded. Now with ZigBee, you'd also need a translation unit from a Wi-Fi or other protocol to ZigBee, but messages will not be of the same type, and the philosophy is quite different with ZigBee. So I'm guessing that the end devices may not be affected. However, the border router, because it would have to implement emulation for ZigBee devices, could run a faulty version of Matter that could be affected. So check the version of Matter that is running in the border router.
I was doing the person before, and I was curious how much of the Matter protocol lies within the hardware that transmits it, as opposed to within the protocol's drivers and software stack.
I'm sorry, can you repeat slower? I didn't quite understand.
I'm curious how much of the Matter protocol lies in the hardware that transmits it, as opposed to the actual software stack that processes the information. Like how much of it is physically done, hardware accelerated.
Okay, so as far as I know, so Matter is an application layer protocol. We are not device manufacturers, so I don't know if they are using hardware acceleration or what type of hardware device manufacturer will actually use. But the bottom line is, because Matter is an application layer protocol, you can just run it on any type of hardware that support this software and this standard.
Interesting. Thank you.